This week we are learning about two different types of t-tests. There is the independent t-test and also the paired t-test. So let's just think about the t-test in general. So the t-test is one of the most common statistical tests in experimental research and in survey research. So the t-test is used when there are two groups and there is a continuous variable for the outcome. So for instance, maybe we are comparing height in both of those groups, or age or weight, or their IQ score in both of those groups, or maybe the score on a depression assessment instrument, or possibly even test scores, how test scores are different in those two groups. But in the most basic experimental setting, the design consists of two groups, a control group. So let's think of two separate groups here where one group is completely independent of another. You cannot be in more than one group. You can only be assigned to only one group. So for instance, in this setting, this design would consist of two groups, a control group and a treatment group. So a control group would get some type of placebo or treatment, for instance, or treatment as usual, and then the treatment group would get some type of innovative intervention that is the focus of the study. And so for instance, maybe there is a new reading program that's being implemented at a school, and so the control group might continue using the same reading program that's normally used at the school, whereas the treatment group would then use the new reading group, the new reading program that's being implemented. And then you can use t-tests to determine if there's any significant differences in their reading scores. If this reading program, this would tell you if this reading program significantly impacted their reading scores. So basically, an independent t-test will answer the following question. Is there a statistically significant difference between the control group and the treatment group? Let's look at an example of an independent t-test. So for instance, Dr. Zan and Dr. Zorders arranged to offer Z-Math, their innovative method for teaching students the multiplication table, to fourth graders at Pico Street School. So let's look at the two groups in this particular study. So students, so for instance, we have, let's pretend that we had 60 total students. And so we can remember the best way to create a sample is through random selection. So let's just say that the names of all 60 fourth graders in the school are written on slips of paper and placed into a hat. And then the principal can randomly draw 30 names from the hat. So these 30 names would be assigned to the control group, and then the remaining 30 would be assigned to the Z-Math group. So for the actual study, from 10 o'clock to 11:30 a.m., which would be the usual time for the daily math lesson, the students in the control group would go to room 14 and they would receive their regular math lesson. And then the students in the Z-Math group would go to room 8 for their Z-Math lesson. And of course, the students who's getting the Z-Math lesson, they cannot share what they're learning with the other students. So after 4 weeks, after a month, all students would be given a test. They would have 10 minutes to write out their entire multiplication table with the solutions on a blank piece of paper. And from there, we could then compare the scores from the control group and the treatment group to see if there are any significant differences. So for our hypotheses for this particular study, for an independent t-test, we can say our null hypothesis would be there is no statistically significant differences in the test scores between the groups. And our H1, our alternative hypothesis, could state the Z math group significantly outperformed the math as usual group. Or your alternative hypothesis could even state, whereas your null stated that there is no significant differences, your alternative could easily say there are significant differences between the test in the test scores between the two groups. So of course there is no finite formula that you have to complete when writing your hypotheses. It just has to make sense. So in this case, this alternative said, you know, alternative would be they significantly outperformed, but we can also say there are significant differences in the test scores between the two groups. Now, for an independent t-test, there are certain assumptions that have to be met in order for your t-test to be robust. So for instance, think about these assumptions as looking both ways before you cross the street. Certainly you could cross the street without looking, but you would probably wind up in much better shape if you looked first. So it's the same thing in terms of statistical tests. Of course, you can run any statistical test on any data without looking at any of the assumptions, but you might end up winding up with misleading findings. You might end up with these results and that might look great. Oh, this is exactly what I'm looking for. But yet, if you look at the assumptions, maybe your data are not normal, or maybe your sample size is too small, etc., etc. So it's always good to make sure that your findings are not misleading. Make sure that your data meet the proper assumptions. So the assumptions for independent t-tests, there are 3 assumptions that should be met. First is normality. So to check for normality, we want to produce a histogram for each of the 2 groups to determine, to make sure that each group has a normal distribution. The second assumption is, so let's stop right there for a second. So let's go ahead and look at this sample set. I'm going to escape out of here for a minute. And if you go into additional resources in Blackboard, you can open up the data set that I'm going to use, the independent t-test example. So let's go ahead and open that up. And we're going to check for normality. We're going to check the normality of each of the groups. Now, what I'm doing this week is going to be a little different from Chapter 9 from your textbook. And so either way, if you want to stick strictly to the way the textbook described how you should complete your t-test, that is perfectly fine. I feel that this is a little easier to understand, a little less, fewer steps to take. So, but I just wanted to let you know that some of the things that I'm doing in SPSS is a little different than what your textbook is explaining this week. But essentially it's the same. So first thing, let's check for normality, and this is one way that we can check for the normality of 2 groups. So remember, you have 2 groups here. This is group 1. Let's go back and look at the variable view here. So group 1 is the control group. Group 2 is the treatment group, ZMath. So the first thing I want to do, I want to check for the normality of group 1, my control group. And the way that we can do that, we can, if you click on this little icon here, this little icon stands for select cases. So go ahead and click on select cases. And if you click on if condition is satisfied, click on if. And now I'm going to say, notice that my group variable is highlighted. And so I only want to check the normality. I only want to focus on the data in group 1. So I'm going to type in group equals 1. And I'm going to click continue. And notice that it says if condition is satisfied, group equals 1. So that means I'm only focusing on my control group here. I'm going to click OK. And notice that it shows right here that I'm filtering out my data. I'm only looking at those that are identified as 1. Now if I go back to my data view, scroll down, and notice that all of the individuals who were part of the treatment group, notice that they're marked out. Okay? And that's basically telling us that it's marked out because we are not looking at this data right now. It's only looking at the control group. So that means now we can go ahead and run, we can create a histogram like we normally would. So let's go to Analyze, Descriptive Statistics, and let's go to Frequencies. Now notice this is my filtered group here, my control group. So I'm going to select this one for my, oh actually, I'm sorry, that's wrong, because group is actually a categorical variable. You cannot create a histogram with a categorical variable. You actually need score. We're going to click on score, but because only our control group is selected, it will only focus on the scores of the control group. So we have score. Let's click on charts. And let's go to histogram, and we also want to show a normal curve on histogram. Continue, and OK. And let's see. Alright, good. So we have a histogram on our first group, and now we want to run a histogram with a normal curve for our second group. So let's go back here. Again, we can go to select cases, and we're going to change it. So instead of group equals 1, we're going to say group equals 2. And now SPSS shows that we're only selecting group 2, our treatment group. And we can even go into our data view and now look and see all of our individuals who were in the control group are now marked out. We're only looking at our treatment group. So again, now we can go ahead and analyze descriptive statistics, frequencies. We can leave score in there because it's okay, because now it's only going to focus on our treatment group. Charts, histograms is still selected with a normal curve. And here is our second histogram. Okay? So we have our first histogram, those who are taking math as usual, and this is for our students who are their scores for those who are taking Z math. So now notice, although the normal curve, this normal curve right here is shorter, it's a little shorter and a little fatter than our other normal curve. But in terms of normality, it's not an issue, okay? Because again, remember, we want to see how symmetrical our distribution is, and this is pretty symmetrical. Okay, so if you slice this curve vertically down the middle, the left side would resemble almost a mirror image of the right side. And the same thing here. If you slice it down the middle, it's a good resemblance of one another. Okay, so going back to our first assumption, normality, it looks like we have met the assumption of normality. Now, the next assumption is homogeneity, and that we will check that the variances, this is when we check if the variances of the two groups are not too different from each other. And so in SPSS is an option selected during the actual run of the t-test where it's going to complete a Levene's test for us. And so how do we determine if the test of homogeneity has been met? If it has a significance p-value greater than 0.05, that means that there is no statistically significant difference between the variances of the groups. That's a good thing. If we want it to be greater than 0.05, that's telling us there's no significant differences, and that would mean that our data would pass the homogeneity of variance test. Okay? So we will run that in a minute whenever we run our analysis. And the third t-test assumption, n should be at least 30 in each group. So again, you can run a t-test with any number in your group. It can be you can have an n of any size, but the larger the n, the more robust the t-test is. So let's go back to our data here. Now notice that this is still marked out. This is still focused on our treatment group, so we need to remove that. So instead of if condition is satisfied, we want to go back to all cases. Click OK, and now it says filter off. So let's go and check real quick though. Good. It's off. Alright, so let's go ahead and run our t-test. So let's go to Analyze, Compare Means, and we are actually going to select a one-way ANOVA. This is a little different from what your textbook shared with you this week, and I think that this is a little bit easier. It's the ANOVA, the one-way ANOVA is a little easier to load, and it actually produces the same report that the independent samples t-test would report. And so basically the difference between a one-way ANOVA and an independent samples t-test, ANOVA, you're comparing 3 or more tests, 3 or more means. Independent samples t-test, you're comparing 2. But essentially, it's the same. It's the same process. It's the same calculation that's going into it. So one-way ANOVA would actually be the same thing, and it's easier to load. So that's what I'm going to use. But again, if you feel more comfortable doing it the way your Chapter 9 explained it, feel free to do so. So I'm going to go ahead and click on one-way ANOVA, and I'm going to move the continuous variable that we want to analyze. So score is what we want to analyze. We're going to move that to the dependent list window, and we want to move the categorical variable into the factor window. Now remember, choose group. This is for all the cases. We don't want to choose the one that's filtered out. So choose group here, and that's going to be our factor. And now let's click on options. And now we're in the one-way ANOVA window, and we're going to check descriptive, homogeneity of variance test, and means plot. And now we can click continue. And now we can click OK for our results. So let's go ahead, before we read our results, let's make sure that our assumptions have been met. So we still need to make sure that our sample size, that we meet our assumption for sample size and our test of homogeneity of variances. So let's look at, this is our Levene's test. And let's look at the last column of the Levene's test. We've used the Levene's statistic before. I think that was in chapter 5. So let's look at the significance value. It's 0.433. And since this is greater than 0.05, this tells us that there is no statistically significant difference between the variances in the score variable from the two groups. So the variances of the two groups are similar. They are not significantly different, which means that which means that the homogeneity of variance assumption has been satisfied. So now we can look at our final item on the checklist, which is N, and that would show right here. N is our sample size, and you can see math as usual. We have an N of 30, Z math an N of 30. So this satisfies the N assumption, stating that each group should have at least 30 people. Now let's look at, notice these are the descriptives for our variables. And notice that the Z math score is higher than, the mean score is higher than the math as usual score. And so you can also, if we scroll down, we have our means plot, and it shows that our students had higher scores, those who had Z math scores. So on the basis of this mean, you could, the first thought that might pop in your mind, you might think, oh, well, that's great. That means that the Z math program is effective, and, these students, this is a great program that the school has implemented. However, we need to look more into it, because we need to make sure that this is not just occurring by chance. So we want to make sure that our findings are significant. So let's look at our significance value here. So we're looking at, this is our ANOVA table, and we want to see between groups, because remember, we're comparing our two independent groups. So our significance level is 0.015. And so basically this tells us that if you would subtract the difference between these two means, that would basically tell us that we would expect to see about a 5.2 difference in the group scores about 1.5% of the time. If I change this to percentage, I could say about 1.5% of the time there would be a 5.2 increase, a 5.2 difference in the group scores, if it was occurring by chance alone. So in other words, based on the data gathered, if ZMath in fact had a null effect, we would see that the ZMath group outperformed the math as usual group by 5.2 points, about 1.5% of the time. So according to our results, there are significant differences, and our Z math group significantly outperforms our math as usual group. So these are our SPSS. This is our SPSS output. Now let's talk about how we would write our results. So basically, you're stating in your results, you're stating what those p-values are. You're going back to, you're connecting that back to your hypothesis. Which hypothesis does this support? So basically, our result says our investigation produced a p-value of 0.015. Since this is less than the alpha level of 0.05, we consider the differences detected between the groups statistically significant, and as such, we reject the null hypothesis, which states there is no significant differences between the groups, and opt for the alternate hypothesis H1, which states that the difference detected between the groups is attributable to the ZMath intervention. And if we had to write an abstract for this, we would first start off with a little context, a little background about sample size and what our study is about. So for our abstract, we can say a group of 60 fourth graders were randomly assigned to one of two groups to determine if ZMath was superior to traditional teaching methods when it comes to learning the multiplication table. After 1 month, students in the ZMath group learned an average of 80.97% of the multiplication table. Now I'm going to stop right there and go back and see, basically this comes from our mean values here. That's what we're plugging in. So ZMath learned an average of 80.97% of the multiplication table, significantly outperforming students taught using traditional methods, who on average learned 75.77% of the multiplication table. P-value 0.05 at an alpha level of 0.005. So that is an example of an independent t-test, pretty straightforward. I'm about to move into the pair t-test, so if you want to pause my lecture for a few minutes, get up, stretch your legs, get a drink of water, get a snack, whatever, go ahead and do so, because I'm going to move straight into the pair t-test. So we just finished talking about an independent t-test, which requires a random assignment of participants. One in a, part of these participants, some of these participants would be in a control group, some would be in a treatment group. Now there's also the pair t-test. The pair t-test provides an alternate approach that can be used to test the effectiveness of an implementation using a single group that does not require a sizable N. So we don't have to have a large N in order to complete a pair t-test. And so, whereas for the independent t-test, we needed to have, those groups needed to have at least 30 each. So that meant you needed to have at least 60 in your entire study. And so if you don't, what if you only have maybe 30 individuals? Well, total. So that would mean you could possibly do a pair t-test where you would, the same group would be used throughout the whole study. And so we're going to talk about how we can do that. And so this type of design, pair t-test, there's different names that can typically be used for this design, but it all essentially means the same thing. You might have heard it called pre-test, post-test design. Sometimes it's called simple time series design. It can possibly be an OXO design, O meaning observation and X meaning treatment. But basically, regardless of all three of these names, it's all the same design, this design consists of only one group. However, this one group goes through 3 different steps. And so step 1 would be the pretest. And this would be some type of Pre-test score, sometimes referred to as the baseline measurement score prior to intervention. It's indicating the level that the participant was prior to exposing him to the treatment. So going back to our ZMath, for instance, if we only had one group and we're about to implement ZMath to this one group, I could have all, my group of students complete some type of pretest. I could have them complete a test on a multiplication test prior to giving them the ZMath program. So I would give them a pretest to get their baseline scores. Step 2 would be the actual treatment. So that would be the intervention. That could be the ZMath program. That could be a change in the condition, training, what have you. And then step 3 would be the post-test. So you would administer the same test used in step 1. So going back to that same ZMath example, pre-test, I can give them a multiplication test before I begin that ZMath program. Step 2, I could implement the ZMath program for a month, and then post-test, after a month, I would give them the exact same multiplication test to see if there is any significant growth over that month, during over the course of that month. So, your paired t-test analysis, whenever we complete this analysis, this is going to give us 3 critical pieces of information. It's going to give us a mean pre-test score, a mean post-test score, and a p-value that will tell us if there are any significant differences between the pre and the post. So if the p-value is less than 0.05, this indicates that there is a statistically significant difference between the pre-test and the post-test score, suggesting that the treatment made an impact. So remember, there's some type of treatment going on here if it's an experimental study. And so you would compare the mean scores, the pre-test to the post-test. And if it is significant, that's telling us that there is some type of impact from the treatment. So let's look at an example of a paired t-test. Acme Industries has 10 people on its production staff. The supervisor is looking for an affordable way to boost productivity and is considering offering unlimited free coffee to the staff. So, would you produce more work if you had free coffee all day long, every day of the week? I'm not a coffee drinker, so I'm not sure if I would or not. But let's look at the groups here for our paired t-test. So remember, our paired t-test, we only need one group. A paired t-test would only function as one group. So one group will consist of 10 members of the production staff. And let's look at the procedure here. Remember, pre-test, treatment, and then post-test. So for the pre-test, the manager, we need our baseline data here, our baseline score. So the manager will count the number of units each staff member processed last week. Now our treatment is manager announces that the staff can have as much coffee as they want at no charge. And then the post-test, at the end of the week, the manager gathers the total number of units that each staff member processed to determine if they had a significant increase in the amount of production, in the amount of units that they produced. So our hypotheses, our null hypothesis, providing the staff with free coffee, that should say will have no impact on productivity. Or alternative hypothesis, providing the staff with free coffee will enhance productivity. Wow, I made the same typo twice. I'm so sorry about that. Now, there's only one assumption for the paired t-test, and that is an assumption of normality of differences. So basically, SPSS will compute a difference between the pretest scores and the post-test scores, and that difference should be normally distributed. And we're going to actually run that. We're going to do that in a minute. I will show you how SPSS can compute a new variable called diff, and which will contain the difference between the pretest scores and the post-test scores. And then from there we can run a histogram with a normal curve for diff and inspect the curve for normality. So let's run a paired t-test. Go ahead and open up the paired t-test example from SPSS. Alright, so let's create the new variable here. So first let's go to, let's select transform and compute variable. And now we're going to, for the target variable, we're going to enter diff. And in the numeric expression, we're going to type in post-test minus pretest. And I'm going to click OK. So that tells me that I now have a new variable called diff, and we can even check our data view, and now you can see that another variable has been added, a diff variable has been added. So column 1 has the name of each staff member, column 2 and 3 we have our pretest, post-test, and now column 4 contains the diff variable. So now it's time to generate the histogram with the normal curve. So as usual, we can go to Analyze, Descriptive Statistics, Frequencies, and now we're going to select diff for our variable and histogram and click OK. And this would be our histogram for diff, which, and actually I forgot to select normal curve with a normal curve. There we go. So I think it's close enough. It's close enough to a normal distribution. So it shows a reasonable symmetrical bell. So we can say that the difference between the pretest and post-test scores meet the criteria of normality. So we've met the assumption. So now let's go ahead and complete our t-test. So to run a paired t-test, let's go to Analyze, Compare Means, and we're going to select Paired Samples. And now we are going to basically move these variables to this right side. So move the pretest variable under variable 1. And we are going to move post-test to variable 2 and click OK. Now the results of this paired t-test are read from two tables. So this table right here, paired sample statistics, it reports the mean for each group. So our pretest mean had a mean of 36.4. Our post-test score is 40.10. And it also shows that we have a sample size of n in each group. Remember, it's our same group. And it shows our standard deviation and standard error mean. Now, we also have our paired samples test here. It focuses on the difference between the pretest and the post-test. So notice this column right here shows that there's a 3.7 difference between the means. So 3.7 difference between these means. And notice our last column shows a significance value of 0.030 for this comparison. And since 0.030 is less than 0.05, we could conclude that there is a statistically significant difference between the post-test and the pre-test scores. So going back to our results, we can say since the p-value 0.030 is less than the specified alpha level of 0.05, this suggests that the 3.7 point increase in productivity from 36.4 to 40.1 is statistically significant. And in terms of the hypotheses, we would reject HO and not reject H1. And to document our results in an abstract, we can state we compared weekly productivity figures the week before and after implementing a free unlimited coffee program. Our 10 staff members processed an average of 3.7 additional cases per week with coffee, up from 36.4 to 40.1, which is statistically significant, p-value of 0.03 at an alpha level of 0.05. So, I hope I did not confuse you this week by showing you a few different steps to complete t-test a little differently from your textbook. Again, I think this is a little more straightforward, a little less complex, and so hopefully you're feeling okay with t-test for this week. So just remember that there's, depending on the criteria, either you would need an independent t-test or a paired t-test.